There it is. Okay, so you are being introduced to the wonderful world of matrices today. Matrices, my absolute favorite topic. I love them all, but this is in my heart of hearts. So those of you who are freshmen taking this course and hopefully continue on the path that you're on will be in the linear algebra course your senior year, and it's all about matrix analysis. So just get excited. Everybody, welcome again to the wonderful world of matrices. Matrices. This is going to allow us to have another way to solve systems. But matrices are huge in the real world. So what is a matrix? A matrix is just a beautiful way of presenting data. So it's just rows and columns of data. It's a data set. It's a table. Our world today is all about data. So every industry collects data and they analyze data and then they optimize solutions to pain points, minimizing cost, maximizing profit, all sorts of things. The internet collects data on all of us, on everything, and everything is represented in this matrix format. But before we start working with matrices, let's just revisit a linear equation in two variables and then demonstrate how to represent this same system using matrices. So let's say there are two orders that are placed at a pizza shop. Order 1 and order 2. Order 1 has 1 small pizza and 3 salads, and it costs $15. Order 2 is 3 small pizzas and 2 salads, which costs $24. You are being asked to determine how much each small pizza and salad costs. So of course, when you have a word problem, you need to define your variables. It doesn't matter. If you are not given the variables to use, it doesn't matter. So in this case, I'm saying let P represent a small pizza, let S represent a salad. You can use X and Y, doesn't matter. Now, if I were to write equations to represent each of these orders, the order 1 was 1 small pizza plus 3 salads equals $15. So that's going to allow us to represent this first equation. Order 2 is 3 pizzas and 2 salads costing $24. So if you wanted to solve this system, by now we should know how to do it. If you don't, well, you better learn sooner than later. We have our 2 equations and we want to solve this using elimination. So we have to choose a variable to eliminate. What variable do you want to eliminate? P. It's isolated, it looks easy. We could have used substitution, but I'm going to eliminate P. How am I going to eliminate P? Well, I'm going to take my first equation and do what to it? Multiply it. Multiply it by -3 so that I have opposite coefficients of P. So I'm going to take the first equation and I'm going to multiply it by -3. So the way I would write that, if I wanted to demonstrate the operation I'm doing, I'd say -3 times equation 1 plus equation 2. I'm just kind of doing a little foreshadowing onto how we're going to start working with matrices in their rows. So I'm going to take that. I'm going to take the second equation. I may want to rewrite this. So now my new first equation is this. Second equation didn't change. And now if I were to add the 2 together, I've eliminated P, and what do I have left over? Okay, and then my next step would be perhaps to divide by -7, and that would give me the value, of S. Now, am I done? No, because the only thing I know is S. So how am I going to solve for the value of P? Okay, so I'm now going to substitute S equals 3 in equation 1. And notice how I'm stating what I'm doing. A lot of y'all didn't do that on the quest. You really need to kind of get in the habit of showing what you're doing at each step. Okay, so I'm taking equation 1. I'm substituting in 3 for S. And so P equals 6, right? Now, this is a word problem, so of course I'm writing my answer as a complete sentence. A salad costs $3 and a small pizza costs $6, right? This is nothing new. This was all what we've already done. You should already be able to do all that. Now, how would I take this same information and represent it as a matrix? Well, remember, I had in our equation, let's just recall our equations. Our system was P, 1P plus 3S equals 15, and 3P plus 2S equals 24. So if I wanted to maybe represent the coefficients of my left-hand side, notice how my first row is my first row of my matrix. The coefficients in my second equation represent the elements in my second row of my matrix. So in other words, these are my coefficients of P, these are my coefficients of S, and each row is an order. So I have columns and I have rows. Does that make sense? Do you see how I've just taken that? So when we have a matrix, when we create a matrix of data, each of the things in the matrix are known as elements. Each of those numbers, and we'll notice that they don't have to be numerical, but in this case, we're dealing with numbers. Our data can be all sorts of things. But in our matrix, each of these entries are known as elements. Now, we refer to something as dimensions. Ugh. The dimensions, and that's plural, dimensions. The dimensions of a matrix is represented by m, the number of rows, and n, the number of columns. It's written as m by n and read m by n. So the dimensions of a matrix is the number of rows by the number of columns. You write the number of rows first, then you write the number of columns. It's like talking about the dimensions of a room, right? The dimensions is the length by the width. So that's in terms of matrices, the number of rows first, then the number of columns. This is very important that you understand. So how many rows does this one have? Row 1, row 2. So number of rows is 2. The number of columns is 2. And I'm just writing R for row and putting a little subscript or indication, and same thing with my columns. Since the number of rows equals the number of columns, it's a very special type of matrix. It is known as a square matrix. The number of rows does not have to equal the number of columns. It depends on the data you've been given. So does everybody understand how I've represented the coefficients as a matrix? Yes? No questions on that? All right. Now, what if I wanted to represent the entire system, meaning I want to include the right-hand side, those little constants? Well, I can write what is known as an augmented matrix an augmented matrix. And an augmented matrix means that I've tacked on another column to include the right-hand side. So if I wanted to take this same original system and represent it as an augmented matrix, my first row would be 1, 3, 15, 3, 2, 24. And normally when we are looking at the coefficient matrix versus the right-hand side, right, this is our coefficient matrix of coefficients, and this is the right-hand side. We normally put a bar or a dotted line to indicate that this is data that represents a system, and the left-hand side are the coefficients, and the last column is the right-hand side. Okay? Now, we have to be very careful before we even write the matrix for the first time that our variables, our equations, are written in the same order. If you put a P and an S in the same column, you're not going to get the right answer. So the very first thing you want to do is rewrite the equation in standard form. If any of your variables are missing, you want to make sure you put a 0 as a placeholder. So again, you want to first make sure that everything is written in standard form, and then you want to include zeros for coefficients of any missing variables. If not, you're performing everything on your operations on the wrong matrix, and there's no way for you to get the right answer. Okay? So let's just practice for fun looking at each of these systems and representing the corresponding augmented matrix. So what do I do first? I check to make sure that my coefficients, my equations are in the same order. I'm good. So I'm going to create a matrix, an augmented matrix, to show the entire system. My first row is 3, 5, -16. My second row is 2, 3, -9. And again, to denote that this is a system, I'm going to just put a little bar there. And what is the dimensions? What are the dimensions? Also known as the order of a matrix, of this matrix. What is the order or dimensions of this matrix? Rows by column. It's always row by column. The number of rows, the number of columns. The number of rows is 2. The number of columns is 3. And again, once you do a lot of these, it becomes second nature. Okay, let's look at the next example. Next example, what do I need to do first? Rewrite it. Rewrite it in the same order, in standard form. So again, if you do not do this, you're going to have a big problem. Now I'm going to write the augmented matrix. What is the first row? The second row? And the order, the dimensions? What is it? 2 by 3. 2 rows, 3 columns. So far, so good? Okay. Now, I said that we could solve systems by using matrices, by augmented matrices. To do that, I need to use the elimination method. Okay? But instead of performing operations on my equations, remember each equation is a row, so I'm going to perform what is known as row operations. Now, what are valid row operations? What can I do to my rows? Well, I could multiply or divide all numbers in a row by a non-zero number. Linear combination, just multiply or divide, multiply the entire row by 2, multiply the entire row by -1/3. Or I could add or subtract all the numbers in one row corresponding to the numbers in another row. That's what we did when we eliminated a variable. Or I could add or subtract a multiple, meaning I multiply one row by a number and then add or subtract, or multiply many, a number, a non-zero number, by both rows and then add or subtract. Your ultimate goal, once you have an augmented matrix, is to get it to the solution matrix. So the solution matrix looks, like this. So we want to get to this, what is known as the solution matrix. The solution matrix, notice, has ones on the main diagonal, and it has zeros above and below it. And then what happens is the right-hand side represents your solution, if it exists. Okay? So let's talk about how we can take a matrix, perform row operations, and get the solution matrix. Again, for this 2x3 system, 2x3 matrix rather, we want it to look like this. Obviously, we can have systems of 3 equations and 3 unknowns that would make a larger augmented matrix with different dimensions. Okay, again, first thing you want to do, very first thing, check to make sure that they're all written in standard form. If not, rewrite it. Is this one in standard form? Yes, so we're good to go. Now I'm going to write the augmented matrix. Step 2 is actually write the augmented matrix. So what is the order of the augmented matrix? What size is it going to be? 2x3, 2 rows, 3 columns. First row, 2, 3, 4. Second row, 1, -2, 9. Just to denote that's a system, I'm going to put a bar there. Could be dotted or solid, it doesn't matter. Now, there's really no definite way you have to arrive at the solution matrix. However, best practice is that you want to try to first a 0 here. However, in some instances, depending on the data of the elements of your matrix, you may want to start with something else. But if there's nothing screaming at you to, hey, do this first, get a 0 there. So if I want to get a 0 there, how would I perform row operations to get a 0 there? So the first thing I want to do is I'm going to rewrite, and this is a very cumbersome process, or it can be. So I'm going to start with my original matrix, and I'm not going to change the first row. I'm going to leave the first row alone, but I want to get a 0 here. So can you tell me how I'm going to use the corresponding coefficient in the first row to get a 0 there? What might I do? Okay, so you're telling me multiply the second second row by -2. So that's -2 times row 2. Yes? And then I'm going to add that to row 1. Okay? Does everybody see how I wrote the operation there? Okay? I'm writing the operation instead of doing an arrow. The arrow means I'm not changing anything. If I have a row operation, I know what my new row is going to be. It's going to be a result of performing this operation. So -2 times row 2 Negative 2 times 1 is negative 2. Negative 2 plus 2 is what? I put it here. Okay, now I'm going to perform the same row operation to the next element in that row. Negative 2 times negative 2 is 4. 4 plus 3 is 7. Do you see how the result of performing that row operation goes in that row? Okay? Yes, yes. Okay, now negative 2 times 9 is negative 18. Negative 18 plus 4 is negative 14. So now I'm here. Now technically you would just keep going, right? But I'm showing every step differently. You do not do every little step differently and rewrite and rewrite and rewrite. You just keep going. Okay, but let's just keep talking about it. Now, the next step, if you didn't see anything screaming at you, would be to get a 0 here. In the first row, second column. Now, I personally would look at this and say, well, why not divide everything in the second row by 7, right? That would get me a 1 in that position in the solution matrix. But let's say you didn't see it. The next thing you would do is look to try to get a 0 here. Okay, so that means I am not changing my second row now, but I need to perform a row operation to get a 0 here. Anybody have any ideas of what I can do? These have to be opposite, right? By 3, right? I agree 100%. Do you see how I wrote that row operation? You need to write your row operations. On the next formal assessment, if you do not indicate what row is not changing and write the explicit row operation, your problem's not done properly. It's not complete. So we have to show all of this. Okay, so let's do it. Negative 7 times row 1. Negative 7 times 2 is negative 14. Negative 14 plus, well, 3 times 0 is 0. So that makes this first entry in the first row negative 14. Now perform the row operation on the second element of the first row. Negative 7 times 3 is negative 21 plus 3 times 7 is 21, so that gives me a 0. Now that was our goal. I mean, you know, we did it. But what is the third element in the first row going to be? There's arithmetic there, right? It's negative 7 times 4 plus 3 times negative 14. All right, so that's negative 28 minus 42, right? It's negative. So you have to be able to do this. So far, so good. Now, again, we would normally just continue on, but I'm going to just rewrite it here because I'm, you know, enumerating every single step. Now, are we at the solution matrix yet? No. What am I missing? I need 1s, right? I need to get 1 here and I need to get 1 here. 1's on my main diagonal. So what could I possibly do to get 1s there? Okay, row 1 divided by negative 14, and then what else? What could I do? We could do this at the same time. Row 2 divided by 7, excellent. Okay, so let's see our new matrix. Okay, negative 14 divided, okay, that's 1, that's 0, And what is the last element? 5. And then I have 0 and 1 and -2. Now remember, these were my coefficients of x. These were my coefficients of y, right? That column, that first column is x. The second column is y. So if I were to rewrite this, it would be, the equation would be x plus 0y equals 5. 0x plus y equals -2. So I have my solution. You see that? Now I could check this, right? I know my solution is the point 5, -2. So since the system has a solution, how would I classify it? Consistent, independent. It has a unique solution. So I could just substitute the x and the y back into the original system, right? And make sure I get true statements, identities. Yeah? All right. Now, what if you got this data? How would you write this data as a matrix? Well, there's many different ways I could do it, right? If I wanted to represent this matrix as a data, this data in a matrix form, the first row would be what? Represent the year. The second row would represent color photos. And the third row would represent black and white photos, right? Make sense? Okay, and then my columns would just correspond to that. So 1980, 82, 51. I mean, if it's organized in this way, look how beautiful. Oh, I didn't make enough space. So we can just transcribe this rather into matrix form. And what are the dimensions? What is the order of this matrix? 3 by 4, 3 rows and 3 columns. And now I'm not putting a bar in here. This isn't a system. This is just data. Now, I can also use matrices to represent figures in the Cartesian plane, in the coordinate plane. So if I wanted to take this data, I could plot points that is represented by this information, connect the vertices, and represent line segments from each point, and then state the figure. So if I wanted to do that, I would be told that each column is a point. Let's call P and Q. P has an X value and a Y value. So the rows represent the X and the Y values. The columns represent the points. So this is point 1. And it is the ordered pair 2, -1. This is point 2. And it represents the ordered pair -3, 5. I would have to tell you what the data represented, but I'm telling you that each column represents a point that consists of an X and a Y value denoted in the rows. Okay, so let's plot these points. I have 2, -1. That's point 1, that's P. And then I have -3, 5, and that's point Q. So if I were to connect those, I'd get this line segment. So imagine how we could draw pictures, right? Yes. Yes. Absolutely. Absolutely. You would just have to explain what the rows and the columns represent. Absolutely. Okay. Let's go ahead and follow the same trend, though, and let's represent the triangle shown here as a matrix. And again, you could tell me that the rows are the points and the columns represent the coefficient or the values of x and y, or vice versa. It doesn't matter. That was an excellent point to bring up. But I'm going to just say this is point 1. And I'm going to call this point 1. And then I'm going to represent point 2. And that's going to be point 2. And then I have point 3. And that's going to be point 3. Oops. Okay, and they each have an x and a y value. So tell me what, well, write the matrix. And let's see if we get the same thing. And then tell me the order. Try to write the matrix and tell me the order. Did you get this to be the matrix? And when you read a matrix, you read the rows by rows. So you read across. Can everybody get this matrix? And that's fine. So you get what's technically the transpose of this, where you interchange the rows and the columns. Yes. What is the order of this matrix? It is a 2 by 3. Very good. Okay, let's keep it going. Woo, here we go. Look at this matrix. Okay, so we have ordered triples now. We have each row represents the x, the y, and the z value of a point. Okay, so I have point 1. What point is that in the x, y, z? It's the origin, right? That's point 1. Then I have point 2. Okay, and we need to plot. We need to be able to plot. So I'm going -2 in the x direction, so back, not to the left or right, not up or down. That's point 2. Actually, let me change these and call these A, B, and C, and D, and stuff like that. Okay, so A, this was point A. This was point B. Okay, now let's plot point C. So I'm going back 2, and then I'm going to the right 2. So about there. And then I have D, not going back or forward in the x direction, but I'm going to the right 2. Are you with me so far? Okay. And then I have E, which is just on the z-axis. And then let's keep it going. Let's say F. F is -2, not to the right or to the left, but up 2. Let's say G. G is back 2, to the right 2, and then up 2. So it's about there. And then last but not least, let's go ahead and use, I'm running out of colors. Well, let's just use fuchsia again. I'm going to the right 2 and then up 2. Okay, so then if I connect these, what shape do I have?
A cube.
A hideous cube, but we get it, right? A cube. All right, so we can use matrices to represent data. It can be geometric. It can be all sorts of things. Let's keep it going. Let's talk about how to now use this, continue on using matrices to solve systems of linear equations. Now, we talked about different ways to solve systems. We also learned that some systems have no solutions. So we can compute the exact solution to a system by using what methods? Do we remember? Substitution. And elimination. And then now we're going to talk about a new method called Gauss-Jordan. Well, actually, let me change that. Let me go ahead and just write our old methods first. So we have substitution and elimination. And now this is going to be, well, linear combination. We didn't talk about that. Third method is going to be Gauss-Jordan. Frederick Gauss originally came up with this, and then it became Gauss-Jordan. This is also known as Gaussian elimination. Now, ultimately, we want to be able to perform row operations to get the solution matrix. So let's see how we would represent the augmented matrix for this system. What would the first row be? Second row. Excellent. Fantastic. And the third row? Excellent. Now, there's your augmented matrix for this system. Now, I'm not going to give you in the spacing all the time, and I may not give you it in standard form. So you got to be careful. All right. Now, what is the order of this matrix? It is a 3 by 4. Remember, it's the number of rows by the number of columns. So let's again go over our matrix row operations and introduce a couple of others. So I am allowed to exchange rows. Maybe one of them is already very close to being the row I want in a solution matrix. So maybe perhaps I would want to move it to another row. I can exchange rows. Now, remember, you're writing all of your row operations. So we have to be able to write the row operation that corresponds to exchanging rows. So let's say I have a row, and I'll call it J. J is just a number, a real number. And I have another row, let's call it K in the matrix. If I'm showing that I'm exchanging rows, you just write this. This is showing that you are exchanging rows. Some people like to actually do it like this and then write, that just to be a little bit more clear. I don't care about that, but I do need to see this. You can, you can swap rows with any matrix depending on what you're trying to do. There are consequences further on in matrix analysis where you're not going to want a row swap, or what you'd have to be a little bit careful about row swapping, but we're not going to need to worry about that in this class. You do want to, we want to see them as the solution matrix, but really if you can identify the X, the Y, and the Z, let's say, of a system, it doesn't really matter where it is. Yeah. But if it says represented as a solution matrix, we do want to see ones on the main diagonal and zeros everywhere else in the coefficient matrix. Now, if I multiply a row by a non-zero constant, we just said we had a row, and I multiply it by a non-zero constant. So I may just want to multiply a row by a number. And then we'd have to specify that A is just an element of the reals, but A is non-zero. Okay, let's say I want to add a non-zero multiple of one row to another row. That's kind of what we were doing. We were showing that we were adding a multiple of one row to another. And again, A cannot equal 0. So we really just introduced exchanging rows and multiplying a row by a non-zero constant. Those are the only two new ones. But there's just more notation. So let's go ahead and work an example from start to finish without being told exactly what steps. You tell me. So I see this beautiful system. What is the first thing I want to do if I want to solve this using Gauss-Jordan, performing row operations on an augmented matrix? Okay, so I check to make sure that they're in standard form. They are. And so now I want to write the augmented matrix. What is the augmented matrix? Okay, that's my, and the order for kicks is a what? It is a 2 by 3. Now remember, the solution matrix, our goal for this one would be this. Right? So that's what we're trying to go for. Now, nothing is screaming at me to do it first. So I'm going to try to get a 0 here. Can anybody tell me row operations that would allow me to do that? Or I could just subtract, right? 2 times. Either way, same thing. Doesn't matter. You just have to tell me what you're doing. Okay, so here we go. First row doesn't change. What is my new second row? Anybody? Yes, and that was our goal. We wanted to get a 0 there. Keep going. What? 7. Yeah. 42. Now, at this point, I could keep trying to get to the solution matrix, or I could maybe simplify each row by dividing it by something. Is there anything that's asking you maybe to simplify? What? Okay, so we want to say row 2 divided by -7. Positive 7, yes. I like to work with smaller numbers because as you perform these row operations, you're multiplying, you have a lot of room for error. So if you can simplify immediately, do it. Why not? Okay, so let me write my new augmented matrix. First row didn't change. Second row is now what? Beautiful. Now, I'm not really there yet. What could I do next? Okay, so you're saying row 1 minus 3 times row 2. Okay, let's do it. Oh, wait, I didn't have them. No, it wasn't. Oh, no. Tell me what my new row 1 is. Zero. 14. Do y'all agree? Yep. And then my second row didn't change. And again, these operations are not unique at all. I mean, some people would have wanted to get that one where the 2 is and divide everything by 2. But then you have fractions. Some people don't like fractions. I mean, there's lots of ways to do these. Now what's next? I have my y. I know my y. Do you know what y is? I know it, right? I know what y is, but I'm not quite there. What do I need to do still? Row 1 divided by 2. Okay, so now I have my row 2 didn't change, but what's my new row 1? Okay, I know my X, I know my Y. If I were to rewrite that, this is telling me that X equals 7 and Y equals 6. Make sense? Okay, I'm going to leave the next two as an exercise for you. So after I do one more example and show you a calculator, how to do this on the calculator, I'm going to let you go back and do these two. So you're coming back to these. Don't think you're ignoring. I mean, why wouldn't you, right? Okay, let's look at what happens when we're solving a system of 3 equations and 3 unknowns used by performing row operations, Gauss-Jordan on an augmented matrix. What's the first thing I do? Okay, make sure that it's in standard form, right? First thing is standard form. Then after I know it's in standard form, I do write the augmented matrix. What is my augmented matrix? Okay, so there's my augmented matrix. Whew! Now, what would I do first? Well, again, if nothing is screaming at you, the best practice is to get a 0 here. Say that again.
Always.
Yeah, it's gonna be very easy. Yeah, to get a 0 there, in my opinion. Okay, that's a very good question. So my solution matrix, if a unique solution exists, is 1s on the main diagonal, 0s everywhere else in the coefficient matrix, and that's going to give me my X, my Y, and my Z. That element of the matrix 0? Oh, let's do that. You want to do that? Let's go ahead and do that. Why not? Why not? We can do whatever we want as long as they're valid row operations. Okay. Oops, sorry about that. I didn't really want to erase all that, but I just did. Okay. So let's say Josh said, what if I interchange these rows? So row 1 interchanged with, let me do capitals. Row 1 interchanged with row 2. Okay. That's fine. So can do that. Now, so that means I want what? I want a 0 here. You do want to try to start getting 0s underneath the main diagonals. Okay, so if I wanted to get a 0 there, what could I do? Well, I want to exploit this 1 because it's very easy to exploit that 1. Okay, so I'm leaving, well, do I have space? I can make space. No, it's not letting me put it there. Okay, I'm writing it on the next row. Let me actually turn my thing sideways and do it this way. Okay, so let's do it. Let's perform that row operation. I didn't change my first row. I didn't change my third row. And you have to be very careful transcribing from matrix to matrix because you can make a mistake and it's a disaster, right? All right, so row 2 minus 3 times row 1. So 3 minus 3 is yay. And then I have 4 minus 3 times 3, which is 9, which is Okay, and then I have 2 minus -3 times 5. So that's 2 plus 15, which is, okay. And then I have 6 plus 21. Okay, is everybody with me so far? Okay, now I really like that 1. I want to exploit that 1 because I can get zeros very easily by utilizing that. So let's get a 0 there. So if I get a 0 there, if I look at my row operation, I'm going to say I'm not changing first row, I'm not changing second row, but what am I going to do utilizing that 1 in row 1 to get that to be a 0? Yes. And let me rewrite it down here. Okay. 1 didn't change. 2 didn't change. And let's perform the row operation. 5 minus 5 is 0. 7 minus 15. -3 plus 25. And then 3 plus 35. Huh? Mm-hmm. Anybody want to do anything in particular next? I'm sorry, I can't hear you. By 2? Is that what you said? Yeah, why not? I mean, if you want to work with smaller numbers, I can leave the first one alone, I can leave the second one alone, and I can divide row 3 by 2. Okay. Oops. Oh, my goodness gracious, sorry. $38 divided by 2. Okay. Now, what am I going to do next? Oh, heaven help me. Well, there's a couple of different things we can do. You can either try to start getting 1s on the main diagonal, maybe dividing everything there by -5. Or if you would prefer to use linear combination, we can start getting 0s here or here. What do you want to do? It doesn't matter. It really doesn't matter. I like to try to get 0s because then once you have a 0, you're closer to that solution matrix and you just divide by a number. What do you want to do? You want to get 0 where? Here? Okay, okay. By doing what? Which row are we going to use? Oops. Okay, which one? Okay, so we're going to do 4 times row 1. Is that what you're saying? Okay, now notice what happens. Well, I'm going to let you do it and see what happens. Okay, what are you telling me to do? I'm not going to give it away. What are you telling me to do? Okay, now if I do that, I'm changing that 1 to a -4. And we. Oh, 1. Well, you told me you wanted a 0 where the 3 was. Yeah. I personally don't have a problem with fractions. I would get 1s immediately. Okay, so can I just tell you that it's in your best interest? Yeah, so I personally would try to get a 1 here. And the way I would do that is I would leave row 1 alone, leave this alone, and divide row 2 by -5. Now, I know you don't like fractions, but really, we're going towards a solution matrix, and your answer may be fractions, so just deal with it. Okay, so then I have 1 here. And yeah, you got a fraction, but it's not going to kill you. Okay. Now, the reason you want to try to get those ones there, if at all possible, is because when you multiply something by 1, right, it's easy to add it to another row and get a 0. So now I don't have a problem getting a 0 here because I can exploit that 1 and that 0 in the second row. So if I wanted to do that, I would leave my row 1 alone. I would leave my row 2 alone. And what might I do to get a 0 where that -4 is? Yes. Okay, so 1 didn't change. 2 didn't change. And what is my new row 3? Now notice what you're doing there. You're doing 4 times -17/5 plus 11, right? Now, I know you don't like this, but you've got to become proficient in doing this. Okay, so -17 times 4 is what? Wait a minute. -4 times -17 is -68/5. And then get a common denominator, right? So if I add those together, what do I really have? Okay. And now I have to do the same thing with the 19, right? So I have 4 times -27/5 plus 19. Okay, and what is that going to give me? -27 times 4 is what? Is what? And then I have to multiply that by 5/5. So 19 times 5. Oh, Josh, you're killing me. Okay, and add those together. What do I have? -101 plus 95 is what? Now, can I get a 1 here? Easily. What do I have to do? Multiply the row by 5. Something went wrong. Some arithmetic went wrong. This is not sitting well with me. And what is this? Something's not right. I'm not agreeing with
Isn't it 108 instead of 101?
Thank you very much. I knew something was wrong. I knew something was wrong. So that would make this 13, which would make this 1. Thank you very much. Arithmetic can kill you. It can kill you. All right, so now I have Z. right? I have Z. Now, if you want to get rid of your fractions, you can get rid of your fractions now. You can right? There's lots of things you could do. I exploit the ones though, or I can exploit this one or this one to get a 0 here. Oops. Golly. So can't we do -3 times row 2 plus row 1? I'm happy with this right now. And I'm definitely happy with this. So if I do -3 times row 2 plus row 1, what do I have? Now you have to do this operation, right? -3 times row 2 plus -5. Do the arithmetic. And what am I going to get there? Anybody? Okay, so this gives me what? This is -51/5 minus 25/5, which gives me -76/5. Oh, positive 21, yes. Mm-hmm. Gosh. And then what about the last element? What are you going to get? And what is the final answer for the right-hand side? Anybody? Do we agree? Okay, now I still need to get a 0 here, which I'm going to use row 3, because how easy would that be? What would our row operations be? Oh my gosh, it doesn't let me erase this. Five 17ths. Wait, no. What are you saying? Row 2 plus 17 fifths, row 3. Okay. No, because -17 fifths plus 17 fifths is 0. So what is my new row 2? Last element. Comes out nicely. What is it? -2. Okay, so I have X, I have Y, I have Z. All I have left is to find X. I'm going to use row 3. What row operations am I going to perform? I'm leaving row 2 alone. I'm leaving row 3 alone. But now I'm doing row 1 minus 26/5 row 3. Does everybody see how to get a 0 there? What am I going to get? 1, 0, 0. It is 4. So my solution is 4, -2, 1. I can substitute it back in and check it. All right, so what I want you to do is I want you to work this system and classify these. So this system would be consistent independent. It has a solution, correct? Then I want you to do this one. The calculator instructions are down here. We'll go over them tomorrow or Wednesday. And I want you to do these, okay? So B, C, and this, I will show you calculator instructions tomorrow if we have time. If not, we'll have to save it again till Friday because we have a longer class on Friday. And then you have a My Math Lab on 6.1. So you have to practice your row operations. Are there any questions before I release you? No? Okay. Y'all have a wonderful rest of your day.